Unlock the potential of artificial intelligence. Welcome to deep learning and generative AI.
Welcome to The Explainer. So, here's a quest for you. Can we build a machine that doesn't just recognize things, but can actually create new things all on its own? Today, we're diving into the brilliant idea behind variational autoencoders, or VAEs for short.
So here's how we're going to break this down. It's really a 5-part story. We'll start with the basic concept, then we'll run headfirst into a problem that seems totally impossible to solve. And then...
All right, first things first, what exactly is a variational autoencoder? To see how they work their magic, we really need to get a handle on the core idea.
Okay, I know, that definition sounds super academic, a real mouthful. But the core concept, it's actually pretty beautiful. Just think of it like this. A VAE is a type of AI that learns to take data, like an image, and crush it down into an abstract recipe. And then it can use that recipe to generate brand new data that has literally never existed before.
So it's basically a 2-part system, right? First, you've got the encoder. Its job is to take an input, let's say a picture of a handwritten number 3, and just squish it. I mean, really compress it down into a tiny summary. But here's the key thing. That summary isn't just one exact point. It's more like a fuzzy cloud of possibilities. Then, the second part, the decoder, comes in. It reaches into that fuzzy cloud, grabs a sample, and its whole goal is to rebuild that original 3 perfectly from scratch.
So, encoder, decoder, squish, and rebuild. Sounds simple enough, right? Well, not quite. This is where we hit the real problem, the huge challenge that VAs were specifically invented to tackle. It's not as simple as it looks. See, the ultimate goal here isn't just to copy and paste, it's to understand the entire landscape of our data. Let me put it this way. If you want to draw a totally new cat that looks real, you can't have just seen one cat, right? You need to understand the very essence of catness. That's what we're trying to do here. We need a map of all possible handwritten digits. And in the world of math, that big, complete map is called the marginal distribution.
Sounds good in theory. I mean, just learn the map of all the data. But in practice, trying to actually calculate this map, well, that's where we run into a giant, show-stopping mathematical wall.
And here is that wall. It's this integral. Basically, to figure out the probability of any one image, the math says we have to consider and add up every single possible recipe that could ever exist in that compressed space. Every single one. Now, for a complex neural network with millions of possibilities, that's not just hard, it is literally impossible. The computers we have today just can't do it. There's a word for this: intractable.
So, are we stuck? Is the whole quest over before it even really started? Nope, because this is where the real genius of VAEs comes into play. If you can't solve a problem directly, you find a clever way around it. Let's look at the first big idea.
So check this out. We can't figure out that super complicated, jagged shape on the left. That's our intractable problem. So what if we don't even try? What if, instead, we just pick a much simpler shape, like that nice, smooth curve on the right, and we just train our AI to make it fit as closely as possible to the real thing? That brilliant workaround? That's called variational inference. Okay, so how do we actually get our simple shape to match the complicated one? We need a goal for our AI to chase, and that's where this thing called the ELBO comes in, the evidence lower bound. Think of it like this. The real answer we want is the ceiling. We can't touch it directly, but we can build a floor, the ELBO, and our goal is to just push that floor up as high as it will go. As we maximize the ELBO, we're automatically shrinking that gap between our approximation and the truth. That gap, by the way, has a name: the KL divergence. And what this all boils down to is this really elegant balancing act. The model is essentially being pulled in 2 directions at once. On one hand, you have the reconstruction term. That part is just screaming, hey, get better at recreating the original image. Make it look perfect. But on the other hand, you have the regularisation term, and it's saying, whoa, hold on, while you're doing that, you have to keep your internal recipe book, that compressed space, super organized and tidy. It's a constant tug of war.
All right, so we have a new goal, a clever objective that gets us around that impossible math problem. Problem solved, right? Well, not so fast. It turns out, in solving one problem, we've stumbled right into a whole new one. Remember that fuzzy cloud of possibilities we talked about? The part where the decoder just randomly picks a point, that random step, that's the new problem. See, the way an AI learns is by sending error signals backward through the network to make tiny adjustments. You can think of these signals as a trail of breadcrumbs called gradients. But that random sampling step, it's like a black hole for those breadcrumbs. The signal goes in and it never comes out. The trail just goes cold. The learning chain is broken.
So how do you fix a broken chain? With another incredibly clever idea, the reparameterization trick. It's so smart. Instead of having a random step inside the network, you pull the randomness outside. You take a predictable output from the encoder, and you combine it with a random number that you generate separately. Just like that, you've made the whole path predictable, or deterministic. The trail of breadcrumbs is complete again, and those learning signals can flow all the way through.
Okay, so let's recap. We faced an impossible calculation, and we found a way around it. Then we hit a broken learning path, and we found a trick to fix it. After all of that, what did we actually get? What's the big payoff for all this hard work? This is the payoff. A normal autoencoder learns a map that's, well, it's patchy. It memorizes the data, but it leaves these huge, empty, dead zones in between. If you try to generate something from one of those dead zones, you just get garbage. But a VA, because of that constant balancing act, learns something totally different. It creates a smooth, continuous map, a beautiful manifold of ideas. And what that means is that any point you pick on this map will generate something new and meaningful. There are no dead zones. So the entire training process really boils down to this simple 5-step loop. An image goes in, we use the reparameterization trick to get a point on our map, we reconstruct the image, we calculate how well we did based on that balancing act, and then we update the network. And it just does this over and over and over again, millions of times, getting a little smarter with every single cycle. So let's zoom out. What are the big takeaways here? Well, the goal was to find a practical way to model really complex data. The innovation, that amazing 1-2 punch of variational inference and the reparameterization trick. But there's always a trade-off, right? The great thing about VAs is that they're really stable to train and they learn this incredible, smooth map of ideas. The flip side is that the images they create can sometimes be a little blurry. And now we know why. It's because the decoder has to learn to create a good enough image from that whole fuzzy cloud of possibilities, so it learns to play it safe and create an average of what it could be, not one single razor-sharp output. And that leaves us with the really fascinating question to chew on. We've just seen how a VAE can create this smooth map for something like handwritten digits. But what else could we map? What if we created a smooth map of musical styles, where you could literally travel from classical to jazz and hear every step in between? Or what about a map of all known chemical compounds, where we could explore the empty spaces to find new life-saving medicines? The whole quest, it turns out, isn't just about creating new images. It's about creating maps for ideas themselves. And that is a pretty amazing thought.